Sushruta for NEET is now available on the Google Play Store. Try it out for free.
Hi students, so good morning again. Um, and today we will continue our discussion with problem solving. Problem solving in the context of electrostatics. Again, you know. So last time we did a set of problems, and this time we're going to do some more problems. Okay. So let me share my screen. So before we go any further, I want to advise all of you students who are now heading back to school to wear masks. This is a very infectious disease. It may not be as dangerous as the Delta variant, but I definitely want to make sure that you students are being very careful. Okay, in as you plan your education, going to school, going to tutorial class, etc. Okay, my advice to you is wear masks all the time whenever you're around people inside any building. Only when you come out and you're not next to people that you take away your mask. Wear it well, make sure it fits well. N95 is always better. N95K, N95, and other you know in masks which are recommended. So please take care of these things, take care of yourself. You don't want to fall sick now, believe me. You don't want to get this virus for no reason. Okay, so having said that, let me now go about discussing electrostatics. So what is important with Gauss law, right, is basically first at the top level you must understand there are many different ideas that flow into the concepts around Gauss law. Okay, now Gauss law in itself may not seem that complicated, you know, but actually it's a very intricate law. Okay, and it ties into um, a lot of calculus that you will not learn till maybe a little bit later. You know, so for instance, Green's theorem, etc. Now, but what you do need to understand, you should understand. Okay, that is the ideas that are held by Gauss's law. Okay, Gauss's law. Gauss was as great a mathematician as you, or some would argue, and a physicist, some would argue, as Newton. Okay, he laid also the foundation of various, as a very young child, he discovered the arithmetic series, you know, and the formula for the arithmetic series as a young child, and his use of mathematics, his use of all the things that we know today, have learned today. He was later, of course, and laid the foundation of what became Maxwell's equation, and what is modern electromagnetic theory. Owes a lot to Gauss, and particularly this electrostatics he dealt with very beautifully, and therefore you should learn it. Now, all students who participate in our program should first know where to get the app. You go to play.google.com and look for Sushruta. If you're a NEET student, if you're a JEE student, you must look for Ramanujan. But NEET students, go to the Play Store and look for com.nyanamarga.sushruta, and you will get the app. Download it, and then you get 2 free weeks. Okay. Now, use the app. Okay, and if you're a class 12 student, you go for Physics2. Okay. Now, we're also readying a CBSE 12 app, which includes maths, physics, chemistry, biology for CBSE students. Now, this is not yet in the market, and it is going to help a lot for students in readying them for the CBSE exam, and we're hoping that they do well. For the JEE students, we have com.yamaka.ramanujan. Download the app, use it for 2 weeks, try it out free, and then purchase it. Okay. So now, if you are working with your school, then your school can give you a promo code, and please use that promo code if your school is providing that. So this is how this works. So this is the formula sheet from your NCERT textbook. Okay. Now, in addition to the NCERT textbook, we also recommend that students purchase a copy of Concepts of Physics by Professor H.C. Verma. This is the standard textbook used by students who prepare for JEE and NEET. Right? There is also DC, Pandey, etc. But the one that we recommend here is essentially Professor Verma's book. Because it is a low-priced book and it has solved examples. You can read the textbook. It's very simply written, etc. Okay. Now, and so here, let me give you the chapter-wise breakdown. Notice that electricity and magnetism and current electricity, and if you include modern optics, right, they occupy a significant part of your NEET exam. Okay. Now, this alone is as big as, say, something like mechanics. Okay. Mechanics we teach very well to the class 11 students, but electrostatics, current electricity, and modern physics are also extremely significant. The last two topics, the heat and thermodynamics and optics, they also have some coverage. Okay, and we do teach that also. Now, you should learn all 6 parts for physics. Don't ignore anything. And if out of the 180, if you make 140, you should be very, very happy. Physics is the toughest of the 3, and unless you prepare very well, getting to 140 out of 180, which is, let's say you got 35 out of 45, you will be in very good shape. Okay, you should do best in biology, and you should spend the least time there also. Okay, you should make 330 plus out of 360 in biology, so that you can do the little more marks in physics. You should make another 150 plus in chemistry, 150 to 160 in chemistry, and you should, and because you will make a little bit less in physics, you should make up for both in biology and chemistry. And so with the 3, you will make 630, 640, 650, something like that. And with 630, you will be able to get into most colleges for NEET. Okay, so that's what I recommend. So you plan accordingly. You have to spend more time on the physics section, less time on biology. What time you get from biology, you have to spend on physics. Okay, so keep that in mind. Now, in the exam, this is for the exam. Okay, when you prepare, what you should do is you have to spend significant amount of time for preparing for physics, but you must be very effective in using that time. Okay, you must invest in certain parts, and you must learn certain things very well. Okay, so and there's a lot of material to cover, and therefore you must spend a lot of time in certain types of material. Electrostatics is as part of electricity and along with electricity and magnetism, between the 4 subjects, the 4 topics, you should make all the as much as marks as you can. Okay, but notice that you should have a much better grounding in your force side, that is the mechanics side, because it is extremely critical to your success. Okay, JEE is a little bit different. Okay, JEE there is actually a little bit less compared to NEET. They test a lot more things and in a lot more ways. Like 15% is on electronic devices. Optics is so significant. Okay, so the it is surprisingly enough, modern physics is so critical there. They test you all sorts of things and they ask you all sorts of difficult questions. So JEE, you won't get that much marks as you think you will get. More questions will go wrong because they are more numerical. Okay, more questions will be tricky because they are trying to trick you. So JEE is a very different animal. JEE, you get to 200 in the JEE means you're very in very good shape. So but then JEE students must spend a lot of time in physics. And it is also important because in addition to doing well, if you end up in, say, one of the engineering like mechanical or electrical or chemical, you will need all the physics that you learned. Okay. Anyway, so you understand conservation of charge, you understand subatomic charge and the quantization of charge. Charge is an electron, it has 1.6 × 10⁻⁹ coulombs. That's the least you can get. There is no charge below that of the electron. Okay, it is quantized as at that level. Okay, so now a centimeter cubed of copper has 2 to the power of 24 electrons, tons of electrons all over the place. Why do we talk about copper? Copper is the most commonly used in the transmission of electricity, right? Why do you need to understand charge? Because a lot of what we do runs on electricity. Anyway, so the first thing you need to understand is Coulombs law, and it's an inverse square law. The force is proportional to the product of the charges, the force of attraction and repulsion between two charges. Like charges repel, unlike attract, is KQ1 Q2 by R square, and it is along the direction that joins the two charges, right? And then there is, if you have say a sphere of charge, etc., there is superposition. You have to do the integration in along two axes, right? So you componentize and then integrate, right? So and in certain maybe some cases some things will cancel out, etc. Just understand how those things work, and so understand how, if you have a line charge, if you have, right, how Coulomb's law will work and how fields work, right? So related to Coulomb's law is this idea of an electric field. Electric field is a vector, just like force is a vector. It is the force per unit charge. Now, if there is only one charge, at this point, if there is a unit charge, what force will it experience? That is the electric field. Okay? So it is the force per unit charge at a particular point in space due to another charge. Okay? And the constant in the case of Coulomb's law is 1/4 pi epsilon naught r. If there is some space in between that has a permittivity, that becomes 1/4 pi epsilon naught epsilon r, right? Okay, so now three charges are placed at 0, d/2 and d. Okay, so remember today is we are now going through the problem solving, right? So now three charges, plus q, at distances 0, d/2 and d, as in the picture. The net force experienced by plus q at x equals 0 is 0, then what is the value of little q, right? So this is what? This is basically Coulomb's law, right? So now this will put a negative force, repulsive force on plus q, right? So this has to produce a attractive force. So if this is plus q, this has to be minus something, right? So this is at a distance d. So it is 1 by d square. So this is closer. So it is 1 by d square by 4, right? So it has to be 1/4 the charge, even 1/4 the charge and negative. So minus q/4 is the correct answer. This is a very simple question. You have to understand superposition of two vectors, right? The force due to this one plus the force due to this one is the force on this one, is the net force is 0. Then you add the two and then you set it to 0, right? Write the force equation, set it to 0. Then you will end up with an equation in Q and Q, right? And therefore you end up with minus Q by 4. Okay, so this was a very simple equation. Now here's another equation. The bob of a simple pendulum has mass 2 kg and a charge of 5 microcoulombs. It is at rest in a uniform electric field. At equilibrium, the angle that the pendulum makes with the vertical, right? So it has a uniform electric field which is horizontal, right? So now look at this picture. You must always draw the picture, right? So now look at where it is. So there's mg, there's t, right? And then there is E times Q, right? So mg you know, right? EQ you know, right? And it's at rest. So you can say that, so what is the angle theta, right? EQ equals T sine theta. That is, if this angle is theta, this angle is theta, therefore T sine theta is the T is component along this direction. So T sine theta equals EQ, where E is the electric field, right? They've given you the electric field, right? 2000, right? Then T cos theta equals mg. So if you divide the two, you therefore eliminate T. Therefore, you have tan theta equals EQ by mg, right? And therefore, theta equals tan inverse of EQ by mg. So E you know 2000, Q you know 5 into 10 to the power of minus 6, divided by m you know 0.002 grams, 0.002 times 10 G, right? So tan inverse of EQ by mg is tan inverse of 0.5 B. So once you answer, you take another second to evaluate what you've done and then go to the next question, typically, you know. So read the question first once and then read it a second time so you understand exactly what's going on and then you answer. Reading questions well is extremely important, particularly because if they trick you with one word, you can trick you with just one word. Right? So electric field, I already discussed. Electric field is the force per unit charge, right? And it's measured in newtons per coulomb, right? And then we discussed the superposition of electric field with one Q1, Q2, Q3. This was a superposition question, right? And really, instead of dealing with force, you could have dealt with force per unit charge, right? So superposition of electric fields, there is a vector sum, right? And therefore, you have to look at it as a vector sum. When you look at, say, a line charge, etc., 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 you also have to look at a vector sum. But many times, when you look at a line charge, etc., you develop what is called a Gaussian surface, right? So that's where we segue into Gauss's law. Okay, electric field is also related to the Gaussian surface. Now, inside a conductor, there is no electric field because there is no charge. Okay, that is the result of Gauss's law. Gauss's law states that, you know, if you have a closed surface, the charge inside produces the resultant. So a Q by epsilon is the resultant flux, right? Therefore, if there is no charge inside, there is no flux, and as a result, there is no electric field inside a conductor if there is no charge inside that conductor. Okay. Now, dV by dr is the voltage, and therefore inside a conductor the voltage will be constant. If the derivative of something is 0, right, then that something is a constant. Therefore the voltage will be constant. And so this is the superposition principle, right? And therefore now the work done is the force times the dot product of the force and the distance over which it is applied, right? And therefore, now when we look at this other term called potential, right? Potential is the work done to move something from infinity to a particular point. Potential at a point is the work done to move something from infinity to that point in a field, right? So we looked at the force side of fields, and now we are looking at the work side of fields. The work side of fields is related to the potential, just like in gravitation. When we discuss gravitation, also we first discuss the gravitation force, and then we discuss the gravitational potential energy. Like that, electrostatic force, and then the electrostatic potential, which is related to the idea of moving something from infinity to a particular point in the space. Remember that electric field at a particular is also at a particular point, the function of a particular point, but is a vector. Electrostatic potential, on the other hand, is a scalar. So it is a related to work. They are just like you have work and energy as as along with force in mechanics. This is also the same thing. Okay, one is gravitational force. This is electrostatic force. Okay, so field theory is um, used in many fields. You know, um, it is used in, there's a temperature field, there is a pressure field, there is a velocity field. I don't know. I have not that much of a mechanical engineer, but they have this Navier-Stokes equation, etc. They also discuss these things in the context of various things. When you go to IC engines and all that, they will deal with all these things. Okay, so now we then introduce the concept of the dipole, right? Dipole is essentially um, the electric dipole is the distance times the charge. Okay, so if you have it separated by 2a and a charge of minus q and a plus q, you need two equal and opposite charges which make up a dipole, and we say the dipole moment is q times 2a, where 2a is the distance, right? So now if you have a dipole in a uniform electric field, the dipole will experience a torque, and it was connected, like, right, because one will be attracted, the other will be repelled. So you have a rotational result, right? So now here he is evaluating the electric field due to a dipole, right? And therefore he is evaluating the electric field due to a dipole at any point in the x-axis. If you say there's a dipole, this is the origin, and along this is q, plus q, and minus q. So as you move along the x-axis, what is the resultant electric field? So you end up with this equation. Okay. Therefore, as x is greater than far greater than a, you end up with this equation. Okay, 1 by x cubed equation. Okay, that is the dipole moment. Dipole decreases as we move away by x to the power of 3, right? And we have this unit called this new term called the dipole moment, which is also a vector. Q times the distance between the negative and the positive charge. The dipole consists of a positive equal and opposite charge separated by a distance 2a, right? Therefore, we call the dipole moment as q times 2a, and it is along from the negative to the positive. So in this case, the dipole moment is positive because the negative is in the negative side, right? Therefore, and the torque is P cross E. Okay, so this is the dipole moment. So what is the corresponding electric field, etc. Right? So dipole moment in a uniform field, P cross E is the torque. We already discussed that, right? Dipole in non-uniform field, net force. You have to do the corresponding calculation for the net force. All right. So now electric field is applied to a dipole. The value, what is the potential energy, right? The torque is P cross E, right? The potential energy is P dot E. Okay, so you have to do the P dot E, and in this case, it is at an angle of 45 degrees. Therefore, the P is what? Dipole moment is 10 to the power of minus 29. The E is 1000. So P, and it's an angle. So what is the potential in the electric dipole? P dot E. Okay, so this is another question. Electric dipole. Electric dipole is placed at an angle to a non-uniform field. Two forces are different at different points cause a torque. There's also a net force as the field is non-uniform. Okay, so you have both. You have both a torque and a force. Dipole explains a torque and a force. Torque as well as a translational force. Okay, so then we introduce the concept of the electrostatic field, right? And the electrostatic field is defined like this. Due to a point charge at a distance r, q by 4 pi epsilon naught r. Previously, when we looked at electric field, q by 4 pi epsilon naught r by r square, and with a vector, from the charge to that point in that direction. Now there's no vector, there's just a potential, right? Q by 4 pi epsilon naught r, right? And the electrostatic potential is the work done for an external force to bring it from infinity to that point, right? So understand the principles very, very carefully, and so you can have between any 2 points you have what is called the electrostatic potential difference, right? And when we move on to electrostatics in the context of a capacitor, we have electrostatic potential difference between the plates of a capacitor, and electrostatic potential is what we eventually becomes your voltage of a battery. And we introduce this other term EMF, right? So it is the work done, superposition applied to potential energy and work, right? So these are all how these ideas add up. Okay, so there is Coulombs law, electric field, electric potential, dipole, and then Gauss's law. Okay, this forms the core of electrostatics, and after that, capacitance. Okay, so you understand these 5 topics, then, and you solve enough problems in these 5 topics, you have electrostatics covered. Okay, so that's how you have to proceed. Spend time, invest time now at this time, because I assume you're a class 12 student. If you're a class 12 student, you have exam coming in 5 months, right, or 4 months, then this is the time to be solving these problems. Okay, fully understand the relationship between all these ideas, and then solve problems involving that. That's what you should be doing. I reduce the ideas and we reteach it so that people become comfortable. Okay, remember that what you learned in class 11 with respect to work, right, gets reapplied in the context of electrostatic potential. Okay, so please understand how these ideas are always related and how they are reused. So electrostatic potential energy is related to the idea of work, right? And therefore, I'm going to move on because, and then there is this path independence. We discussed path independence before, and we are again discussing path independence in this context. So if you are in an electrostatic field, right, you go from point A to point B. In any conservative field, what is a conservative field? It's a field where the force is essentially a position of r, is a function of r, right? You have a conservative field, in which case you have path independence, which means that you can go any route between 2 points, but the net work will be the same. That is what path independence means, right? So total work done, whether you go A, B, C, or A, B, C, or A, D, C, or straight A to C, the same work will be done. Okay, so that is maybe unintuitive, but in a conservative force, you have a path independence. Conservative force is 1 f of r, right? Therefore, that's what you have to understand, right? And therefore, you also have to understand how to go from electric field to electrostatic potential. dV by dr is the electric field. The gradient of the electrostatic potential is the electric field, right? Therefore, so these things you must understand, you must learn, and you should learn it well. And we teach it the first time in great detail, and the second time now we are going through it at a rapid pace so that you have revised all this. Okay, so now when you revise all this, right, you should have seen all this, you have got it in the app, you know. Now you can see the potential, just like we evaluated the electric field due to multiple charges at a point, you can also evaluate the electrostatic potential due to multiple charges, q by 4 pi epsilon naught r. Just add them up and you will get a result. Only difference is that this is a sum of three scalars in this case. It's not a vector sum. Okay, so it's a scalar value, right? So and then just add up the three values and you will end up with the answer. Okay, so so there is a uniform electric field in a region. The potential at various points on a small sphere centered at P in the region is found to vary between this and this. What is the potential at a point on the sphere whose radius vector makes an angle 60 degrees with the direction of the field? Okay, so there is a uniform electrostatic field in a region. What does that mean? That the electric field is constant in a region. The potential at various points on a small sphere in the region is found to vary. What is the potential at a point on the sphere whose radius vector makes an angle 60 degrees, right? So now the maximum potential difference is 0.8, right? So if the maximum potential difference is 0.8, right? So that is E times D, right? Now, but then the potential difference is also at an angle. If the field is at an angle, right? So you also have to introduce that. So the maximum potential difference is E times D. E dot dl is the potential difference. Here the integral of E dot dl, right? And dl will become D. So E times D is 0.8. So 0.8 is therefore, and it is at an angle 60 degrees. So 0.8 times 60 will give you the potential difference. So the so cos 60 is what? Cos 60 is half, right? So cos 60 is half, right? Makes an angle 60 degrees the direction of the field, therefore it is halved, right? Therefore you will have V as 598.4. Okay, so this is a simple problem, but again you must understand the relationship between electrostatic potential and electric field. Okay, so that's what they're asking. Now, Gauss' law is like this. We already discussed Gauss' law in great detail in all the lectures before. The flux which is defined as the amount of, you can think of it as the amount that of flow, flux is like a flow over a closed Gaussian surface. The flux over a closed Gaussian surface of E dot dA will equal Q by epsilon, the enclosed charge by epsilon. Okay, that is Gauss's law as it's taught in high school. Okay, so E dot dA closed surface integral equals Q by epsilon. If I have a charge, build any surface, any closed surface, the closed integral of E dot dA over that surface will produce the charge divided by epsilon. That's a beautiful law, right? And very counterintuitive, but if you have a small surface, big surface, you still end up with the same flux, which is obvious in some ways, right? Because if you assume it's radiating like that, the amount that radiates is the same, and it is given by Q by epsilon. Okay, so you can, if you had a small sphere or a big sphere, you had a cylinder, you made a cylindrical surface as a Gaussian surface, etc., etc. So keep that in mind. Closed integral of E dot dA equals Q by epsilon. There is a divergence theorem. Let's not confuse you with divergence theorem. Okay. So, but then in each case, you need to understand dA. dA is always normal to a particular surface. So if you had a cylinder like this, and then you have the radius like that, the dA will be perpendicular. dA is a vector. Okay, if you on the cylinder, dA will always be normal in each case to the surface. So when you evaluate it, you must keep that in mind. So vector, it's a vector area. We define it as a vector area. See, notice vector area, then n is normal vector. Okay, so you must learn this. Vector area is normal to the surface, the same as the physical area of the surface. So you must learn this perfectly and understand this, and then use that to solve the problems. Okay, what is the net flux to a closed cube in uniform field? 6 surfaces for a cube, right? If there's a closed cube with no charge inside, 0, because there's no enclosed charge. Enclosed, it has to be enclosed. That's why we said that if you had a metal sphere, inside there will be no electric field. Okay, so understand Gauss law. Okay, once you understand net flux is 0 as there's no charge inside. Okay, those things you must understand, you must get it right. Then when you do the integration, you must know what is the best way to do the integration. R, dr, d phi, sometimes you have to use polar coordinates. You must learn to do integration using polar coordinates. If you learn to do that, then a lot of your life may become a little bit simpler, right? So now here's this point charge, and then he has made a. You can make any kind of Gaussian surface. The trick is to make the correct kind to simplify your problem. Okay, so he has a point charge. Typically, you make a spherical Gaussian surface. So what is the area of the spherical Gaussian surface? What is the direction of the A and the direction of the field will be the same. Okay, that is the interesting thing with spherical Gaussian surface with a point charge, right? dA and E are in the same direction. So E dot dA is just EdA, E times dA. And when you have, if you had at all these points, because of symmetry, because it's spherical, the same distance away, all the E's are constant. Therefore, it just becomes an integral dA. And because it becomes an E dot dA becomes just an integral dA of a surface, spherical surface is 4 pi r square. So E dot 4 pi r square equals q by epsilon naught. Therefore, you have 1 by 4 pi epsilon naught r square. Q by 4 pi epsilon naught r square. Okay, so that's the important idea. That's how you also get the equation. Okay, so so learn to use the laws, use the theory, and then be able to solve the problems, right? So now if you have 3 surfaces, how it will look, this is how it will look, right? So look at the enclosed charge. Okay, so simple application of Gauss law inside a controller. Inside a controller, the electric field is 0. Why? Because there is no enclosed charge. All the charge goes to the surface. Okay, so because the charges are free to move, so they'll always go to the furthest distance from where they cannot go anywhere. Okay, so they'll go to the greatest distance, and therefore that means that they'll move to the surface of the sphere. Okay, so we explained the Gauss's law in the context of spheres. Okay, so calculate the electric flux through S1 and S2. Right. So now he has multiple charges, right? So this one, S1 has a net charge, a net enclosed charge of 0. So the net flux of S1 is 0. This one has net flux. The net enclosed charge is minus Q. S2 has net enclosed charge of minus Q. So the net flux will be minus Q by epsilon naught. Okay. So what is the enclosed charge? And then you use that to understand Gauss's law. Okay. So so that's the important set of ideas here. And so with that, see, today I'm going to stop a little bit early so that you digest the material. Okay. Once you digest the material, you try to do the problems, use Gauss law when needed. You understand electrostatic potential, understand charge, understand how to do problems involving Coulombs law. using electric charge, and when using Gauss's law. Okay, so Gauss's law you must learn to apply. You must use field outside a spherical charge conductor. So then again, you must do the necessary integration. You must know the way you do the integration is very, very critical in Gauss's law. Okay, how do you construct that surface? You must be very intelligent in constructing those surfaces. Once you're intelligent in constructing those surfaces, you have to use the symmetry of the problem to solve a lot of problems in Gauss's law. Okay, so understand that, then things get a lot simpler. Okay, so so if you have a line charge, what do? You create a cylindrical Gaussian surface. Okay, then you integrate at that point. Okay, so let's say you have a line charge like this. In this case, what he doesn't use a Gaussian surface, he just uses integration, standard integration, right? And he says that what will the field be at this point? You have a very long, infinitely long line charge close to this point, right? This and that, this direction electric fields will cancel, and in the horizontal component of the electric field will be additive. So you just add up the integrate for the horizontal component, that is the component along that direction, due to every little delta length. Every dl will have a lambda times dz, because it's a charge per unit length. Lambda times dz is dq, right? Therefore, use that dq to then produce the result. So here he has lambda dz and integral between minus infinity plus infinity of dz, right? Then you solve correspondingly. So he ends up with the E as lambda by 2 pi epsilon naught r. Okay, so do this. This is a simple line integral. He doesn't use Gauss's law, just use the integration. Use standard integration to solve for the electric field. So you can use that too, but sometimes you have to use Gauss's law, right? Same problem using Gauss's law, you use the cylindrical surface, then you end up with the same answer. Cylindrical surface, right? What is the enclosed charge in that cylindrical surface, right? Therefore, the enclosed charge is what? Right? Q by epsilon. Q is lambda times L by epsilon is equal to E times 2 pi r L, right? Therefore, you have lambda by 2 pi r epsilon. Same answer, but using Gauss's law. Okay, so two methods, as I said, cylindrical surface, right? Create the cylindrical surface. Now, what happens in here and here, right? Here and here, why isn't there an E dot dA for the top and bottom of the cylindrical surface? The top and bottom of the cylindrical surface don't have an ER, because the E is always like this and the dA is always like that. So the dot product of two vectors which are 90 degrees is always 0. So as a result, the top and the bottom don't produce any result, but only this part of the cylinder has a E dot dA. The top and bottom, no is E dot dA is 0, because E and dA are perpendicular to each other. Okay. So with that, I'm going to stop, and what I'm going to tell you to do is I'm going to tell you to do all kinds of problems involving this problem. You try the region between two concentric spheres of radii A and B have volume charge density. The value of A such that the electric field in the region between the spheres is constant, right? Okay, so here's what's happening. Inside, right, there is nothing. Then there is this constant area. Now, in this constant area, there is volume charge with a charge density of AR, rho times AR. Okay. So now, so that is the volume charge density is proportional to the radius, constant times the radius. Okay. So now he's asking, what is the value of A such that the electric field, the region between the spheres, will be constant? So between here and here, when will the electric field be constant? So now you pick a Gaussian surface somewhere in between and look at that electric field, right? Now, the electric field in that spherical Gaussian surface, which is somewhere in between A and B, right? What is the enclosed charge? Q enclosed, that divided by epsilon will give you E dot dA, right? You know that by symmetry, the E and the dA will have the same direction, right? So what you do then is A by rho is charge density A by R. So A by R 4 pi R square dr, right? So 4 pi R square dr is what? That is the surface. It is like, so you are basically evaluating the Q enclosed between here and here. Okay, evaluating the Q enclosed between here and here. Okay, and so what is the Q enclosed between here and here? A by R times 4 pi R square dr between A and R. This is the Q enclosed. Okay, there, and that becomes Q plus 2 pi AR square minus 2 pi AA square, right? That is equal to E dot dA. This is 4 pi R square. 4 pi R, 4 pi R square, E times 4 pi R square, right? E dot dA is E times 4 pi R square. That is equal to this. So now Q minus 2 pi A. So so um, um, so Q minus 2 pi AA square will equal 0. Therefore, E will equal Q by 2 pi A square. Okay, so that's how you evaluate it. You evaluate using Gauss's law. Okay, so you create a Gaussian surface at a distance r, and then you do E dot dA equals Q by epsilon. That's it, and use the symmetry to solve the Q by 2 pi A square. All right. So with that, I'm going to stop for today, and then we'll continue next class. Um, next class we will continue a little bit with capacitance, and then we'll move on to other topics. But we really are going at a very fast pace. This is not where you learn. You should learn by looking at getting the app and looking at IIT and you learn by doing more and more problems. So this is a 1 hour quick refresher at best. And we do this so that we do some problems so that you get the hang of what we are doing. My suggestion is you go to HCR, look at the solved problems, and then solve the unsolved problems there, and then look at the JE problems by you downloading using our downloaded app. That's how you build expertise, and you keep building expertise. Eventually, you will feel comfortable and be able to solve all the problems. You have to study. Without studying, nothing happens. Okay, we cannot spoon feed you, and if we told you we can spoon feed you, really we are doing you a disservice. With that, I'm going to end today, and I'll see you all again next week. If it's Sunday morning, it's class 12. If it is Saturday morning, it is class 11. And we ready students for both 11 and 12 material. Okay, so that I'll see you again next week. Thank you.